everyone, and let me just go off with this. Um, this slides had been prepared quite some time back, so there are some issues with that, but let's just go ahead with this one. So this is another area called quantum cryptography, which is again a wrong nomenclature. It should technically be called quantum key distribution. You will understand when I go through slowly why this is so and all that stuff. So there are two good books. In fact, this is a book which a much older book. There are a lot more books which are called quantum computation, but this is a good book which pretty much gives a lot of mathematics, algorithms, and stuff on that. And it's also fairly affordable book. If someone is really serious, you can get hold of your own copy of this. The Indian edition is available for this. This is more talking of a history. The Simon Singh's book is more talking of the history of how coding and all started. So first thing, let's go like everybody needs secrets. There are always secrets. There are military secrets where there are communiques, datas, photos. There are also government secrets, confidential reports, question papers have to be secret till the exam starts and all that stuff. And there are also secrets for everybody. I mean, our bank accounts, credit card should not become a public knowledge. Only authorized people should get it. So question is, how do we maintaining is easy. Put them in a sealed cover and put it inside a bureau, but that doesn't help because we need to take it across and use it, otherwise there is no point. So there has to be some point where I take my data, I give my data only to the bank and not to others, and these kind of things. So that's a question of how we handle that part. Okay, so there are several methods of handling secrets. So one method is trusted courier. Okay, in case of modern technology, it will be a dedicated phone line. Typically, your ATMs are connected to the bank branch through a dedicated phone line. Okay, and assuming that nobody can uh, tap it or listen to it, kind of thing. Okay, and in the earlier days, you always had a trusted courier who would carry it, hiding it. You know, all those Chinese movies with the Chinese things, fellow shaves his head and writes secret on it and all that stuff. The second method is encryption. Okay, encryption means that you hide your message in a kind of a secret language that only the authorized person can understand it. The others, so even now you don't have to really worry about a trusted courier. Okay, trusted courier can lose the secret, everything. Even if he or she loses the message, the other fellow cannot make sense of the message because the message is written in a language only you and the other party can understand. Okay, but then messages are usually written in a normal language, so you hide it in a somewhat secret fashion, and so that the only other person can understand. And the history is pretty old. So one of the earliest records, it says, is from 200 BC. A Greek guy called Polybius wrote something like that. This is a simple technology. So if I want to write his own name, Polybius, so I want P is here. So I replace P with two numbers with the row and the column. So R and D will become P. T and D would respect to T and D would be O, kind of thing. So I only send this part to the sender, and anyone else who does not have access to this particular square cannot make sense of what is this. And only the authorized fellow will have this square. And more importantly, I keep changing this square for each of my recipients. I have a different square, so a different coding scheme. So things are not very common. I'm sure around the same time Arthashastra was written, Kautilya's Arthashastra, probably that also talks of how to send secret coded messages. I don't know, although I don't know if there was some serious thing written in that. Julius Caesar apparently had a slightly different method where it's called the Caesar shift. So every letter of the alphabet gets shifted by a few letters after it. Like every letter becomes three. So for example, T goes TUVW, three letters off, so that becomes W. Similarly, H becomes three letters off, E becomes three letters off. So this phrase, the Caesar shift, would actually look like this, and someone who doesn't know how many letters it has been transmitted cannot make sense of it. Of course, one can painstakingly sit and calculate, do everything till the sentence makes some sense, but well, it takes time. So usually the attack would have happened much before that. The other fellow can do it. This is another classic example. There's a Arthur Conan Doyle story in the Sherlock Holmes adventures. There's one particular adventure where it goes on to say that there was an English gentleman, and in his garden somebody would come in the middle of the night and write these kind of figures, dancing men, and every time that happens his wife would get very scared and doesn't know what happened, kind of thing. So he comes to Sherlock Holmes asking, there's some such mystery going on. The story is called The Mystery of the Dancing Man, and Sherlock Holmes solves it in a very ingenious way. What he does is, luckily for him, he gets several such messages, and the owner of this house meticulously copies all these messages and brings it to Sherlock Holmes. Holmes himself doesn't go and investigate. So what Sherlock Holmes says is that, let's assume that this is in a normal English language, and then he does a statistical analysis. He finds out which figure occurs most in all of the messages, and because he knows that in a normal English language the letter E occurs maximum number of times, so he maps that figure to E. The next maximum occurring letter in the English language is T, so the second maximally occurring figure gets mapped to T and to S, and so on and so forth. So basically he does a frequency analysis, and then he is able to decipher all the messages. So this is a frequency of letters in modern Indian English language, normal English language, rather Victorian English language. Things would have changed a little bit, but not too much. If I have to think of some other language like French or German, this frequency would be different. But the basic point, the moral of the story is that any coding scheme is usually vulnerable to a frequency analysis. And if any of you have seen this movie about the Enigma being built, the imitation game. So if you have seen the imitation game, you will find that finally they realize that every message, German message, would start with something called Hail Hitler. So they map Hail Hitler to the encrypted message, and that's how apparently they break the Enigma. So something repeated always is a vulnerable thing because you can make out. However, in 1926 itself, there was a guy called Gilbert Vernon working in AT&T, and then he thought of a thing called a one-time keypad, so that you have an encryption scheme that you use only once. Okay, in fact, that was the basic thing of Enigma machine. So what happened in Enigma machine is that the Germans invented a typewriter where they would change the pattern in which the mechanical, you have to realize that all of this were happening in a mechanical situation, so it was not easy to make things which gets replaceable. So although I would type normal German language, let's say the QWERTY keyboard, what actually gets typed would be different because every time it gets a different substitution, and the typists in the typing pool would not know what is the substitution. So they would be told, you put the wheel 1, wheel number 32, wheel number 42 kind of thing, and the other fellow should know what it is. So it was called a one-time keypad. I'll explain a little more in the later slides. And in 1949, Shannon wrote a series of papers on mathematical theory of communication, one of which is what I talked in the morning, There was also another one where he showed that a one-time keypad is very secure. So it's like this. In the modern digital language, we'll write like this. So M is my message, M is my message, and K is a key. And key, let us say everything in the digital language, then this is a set of zeros and ones. This is also a set of zeros and ones, but this is a perfectly random set of zeros and ones. And K is of the same length as M. And Shannon says that if you do this, this is your standard Boolean summation, and if you do M plus K and get a encrypted message C, the cipher text, and if M and K are equal length, and if K is used only once, there is no way of cracking this code. That is what Shannon proved it mathematically. And every time you use a different K. Okay, so you can use this happily, and you give this key to the other fellow, and what he has to do, because the digital addition, the Boolean addition is symmetric, you simply add it again, and then you will get back the message. C plus K becomes M, because 1 plus 1 is 0, so in the modulo 2 arithmetic, it's a cyclical addition. Okay, which is well and good, mathematically very secure, proven to be secure. The only problem is that of course, if the other person also should have access to K, okay, and me and the other guy should have the same K, and he should know a priori which K I'm using, which that problem can be solved. I can always tell him, call up the phone and then say I'm using code number 32, code number 26, and like that, and he can use the same thing. But the problem is that we two are physically away, which means that both of us should share a set of keys. And this is used. There are certain banks where Europe it's usually used, where you go to the bank and then he will give you a whole set of 10 or 20, as much as you ask, keypads. You come home, you scratch, and then there is a keypad written, and you use that keypad, and in fact that is the whole idea of your one-time password. Of course, one-time password is used more as a authentication, but I can also use a one-time keypad which can be transmitted. The big problem that happens here is that I can lose the keypads, or somebody can steal the keypads from me, or somebody can make a copy of the keypads and intercept the message, and that person also will have access to the whole message. So there is no more secret. Okay, so of course there are other parts which came in. National Bureau of Standards came up with these are all called symmetric encryption, because I add the key and then the other fellow adds the same key, so you get a the same key is used both by the transmitter and the receiver, so it is called a symmetric encryption. In 1978, these three people in MIT came up with a nice idea, Rivest, Shamir, and Adelman. This is also a symmetric encryption. This is still not, I'm still giving you an idea of classical cryptographic schemes that has been used. I haven't gone to the quantum cryptography yet. I'll come to that later. So RSA and its variants are still being used even today. Okay, let me just see if RSA works. Okay, but I'll come to that part. So the idea how this is basically built on a very solid number theory. So mathematics, pure mathematics, although most of the people think it's not much of use, there are times when pure mathematics becomes very, very useful, like applications come up. So the idea is that you take a very large, two large prime numbers, okay, P and Q, call them P and Q, and compute the product of the two, call that as N, and then you also compute D such that there are two more numbers such that D into E. I think there's some problem here, but I'll come to that because I have not told you what is E. I have messed it up somewhere. Okay. let me look up that part. Okay, but this is something you look up at RSA key. What is RSA key? You can get enough information. So you calculate, you do a modulo arithmetic involving P and Q, and then you find D and E, and you send E and N across public channel. You can happily transmit it over radio. Okay. And then the message is taken to be M, and ciphertext, that is a crypted message, is calculated as C equal to M power E modulo N. This is modulo arithmetic. Okay. And so if you look at this, there is something interesting. From P and Q, we have calculated D and E. Okay, and now we are using D and E, and the transmitter uses E and the receiver uses D. So both of them are not using the same key. So you can happily, you have to exchange different sets of key. The transmitter has one set of key, the receiver has another set of key. These are called one-sided functions. They are not symmetric. Okay, and the whole idea here is that if somebody gets N and E, remember it's not N and P, it's N and E. So E is a function of P, and therefore this thing is bad. Let me just see if I can get to a show you actually. Go to any bank, not card, sorry. Let's just go to SBI. Are you able to see this SBI website that I have opened? Are you able to see?
Yes, sir. Yes, sir.
Yeah. So if you see it here, there's a lock symbol. Okay. And this lock symbol is closed. It's a closed lock symbol. If I open any other this thing, it will be a open lock symbol. Okay. No, my God, I don't know which one gives you. For me, Google also goes into HTTPS. Anyway, it doesn't matter. So the whole idea is that whenever you do any kind of banking transactions, you always have to look for this. Make sure that this is a lockbook symbol, and then when you come here, it says view site information. If you click on it, it has to tell you that connection is secure. If it is not there, don't give your credit card numbers, don't fill your account numbers, any of those things, unless it says secure. If it's an open lock symbol, depending on the browser, that lock symbol will be somewhere else, but always click on it. And then if you go to this certificate, it will tell you somewhere here that it's a so here it says DigiCert EV RSA CA-G2. So this is some variant of an RSA key. Okay, and basically how this happens is that there is a company, it will be said it is signed by VeriSign. No, this is issuer, it doesn't say here, but this is usually typically a company like VeriSign. Sign given to this fellow. So somewhere they will tell you what company takes care of this thing. Okay, so usually there's a company which specializes in taking care of this encryption key. So what happens is, now the moment I log into SBI or the railway booking or the Make My Trip kind of thing, they connect to the VeriSign company. Let's say a company called VeriSign. VeriSign in its bank of computers has two large prime numbers already calculated, made sure that they are prime numbers. They spend a lot of money on mathematicians who will write a code to check whether it's a prime number or not, and then they have a whole library of prime numbers. So they randomly pick two prime numbers, and then they calculate N, D and E from that one, and they will send it to your computer. So the Java backend on my browser will do the calculations to encrypt my credit card details and send it to VeriSign, not to railways. If I'm booking a railway ticket, the railways will never have access to your credit card number. The VeriSign will cross-check and decrypt your credit card number, and they check it with the Visa or MasterCard, and and that information goes between these three companies, and Visa or Mastercard will uh, authenticate the railways to tell that okay, this credit card is valid, and you can start the booking thing. I mean, all these things happen via the Java programming, so you will never know that it's all happening. The railways doesn't know what's happening, SBI doesn't know what is happening, all those things. Okay, so and for this, of course, IRCTC or SBI is going to pay some service charge to VeriSign and all those that company. So the credit card validation has to be done on a service. The company does a credit card validation, but all the while the numbers are going in an encrypted mode using the RSA key, so that if somebody intercepts your internet packets that is going from your computer to the railway's computer, they cannot in principle make out your credit card number or the CVV code and those kind of things. Okay, so every time you do the transactions, you make sure at least check the certificate, even if you don't understand that there is a lock symbol, a closed lock symbol, and it's secure. I showed that because these pictures are somehow not good. This was taken, screenshots were taken long back. Anyway, so there are variations of the RSA. So the whole idea that it banks on in this, that if I give you P and Q, you can take a calculator and enter P, enter Q, and then find out N. Okay, it's very easy. Within a few microseconds, you will get N. But if I give you N and ask to find P and Q, that is the factorization, that takes a very, very long time, even in advanced computers. Okay, a factorization problem is not a straightforward problem. So given a small number like 6, you can tell 2 and 3 are factors. 9, you say 3 is a factor. 15, you say 3 and 5 are a factors. But the further and further I go, it becomes more and more difficult. And it's always not this. There are some numbers which has more than one set of prime factors. So which pair I am using is also a question that comes into picture. So it takes several days. In fact, it takes a couple of months to factorize very large n, and computational time goes exponentially as n. The higher the n, it goes even larger and larger on the computational time. So all that people are now, we are all feeling safe on that, is that even if somebody intercepts the communication between me and SBI and wherever, it would take that person several months before cracking my password. And that is one of the reasons why all of them keep telling you that every once in 6 months or something you change your password. So even if somebody has stolen the communication from you, uh, by the time he or she analyzes and gets your password, you would have changed the password over here. So that is why this is. But however, there's no mathematical proof to say there is no easy way to factorize P and Q. Mathematicians are still working on. They have come up with some methods, but it's still not worked out. And the other thing, this is even more important. Nobody has said that the only way to crack RSA is to factorize P and Q. Okay, so till now, challenge is open. There are people who are trying out. This is not hacking. This is just to crack. Hacking is to get into your computer and get information. This is to crack the encrypted, to decrypt the RSA key. And there is no theory which says to order to crack RSA, I have to get the P and Q. So somebody may come up with another function which overturns all these things, and then this whole methodology will not be secure. So the RSA key as of now is computationally secure. But then the quantum computational people, so particularly this guy Shor, he came up with an algorithm which says that if I have a quantum computer, then if I put a factorization part on it, on a normal regular computer, I'll have to check every number whether it's a factor. I'll have to do at least square root of n methods, n by 2 methods, whereas the algorithm, Shor's algorithm, reduces the time taken is actually a wrong statement. Basically, it has lesser number of computational steps than a normal sequential factorizing of n. So the whole, so if and when somebody builds a full-fledged quantum computer and it becomes easily available, and then somebody with an access to quantum computer will tap the communication between your computer and your bank, and then he can get it, and there is a finite possibility that that guy gets access to your bank password before you know that it has been done. So what is the, I mean, at least as a mark of telling this, two people in 1984 gave a alternate methodology. Name was Charles Bennet and Gilles Brassard, both of them working in, one of them in New York, the other one is in Canada, University of Montreal, and this was first presented in a conference in Bangalore in 1984 in Indian Institute of Science. The conference was hosted in Indian Institute of Science, and so it was dubbed as a Bennet and Brassard 84 methodology. So what I'm going to tell you now is to explain to you Bennet Brassard 84 methodology. For a very long time, not many people took it seriously. Half of them were engineers. They didn't even, computer scientists, they didn't even understand the relevance of quantum mechanics. But let me explain to you. So now in the past 2-3 years, it's become another buzzword of quantum cryptography. Government is also putting a lot of money, and defense labs have been trying. There's a lot of methodologies have been, people are onto it, and this is one of the successful quantum applications of quantum mechanics, I should say. Okay, so let's go again from a little bit of basics, so I make sure that people understand everything. So this is your normal digital communication. So a TTL pulse 5 volts is 1. Well, this part is a bit fuzzy, but less than something is 0. So this is 1 1 1 0 0. I think this is okay. 0 1 0 0. Okay, so that is my data, and pulse is on, digital 1, no pulse, digital off. I can also do the same thing, same repetition of this and fiber optic communication. All I do is to send this to an LED, and whenever the pulse is high, LED will become on, pulse is low, LED is off, and so this is somewhat it looks like. And so this can be transmitted via fibers, and the other side there is a photodetector which converts the light signal into the same electrical signal, and everything is nice and good. Okay, so there is one more methodology where I can use the polarization of light. Polarization is basically the light is traveling, and how is the electromagnetic field oscillating? If you remember your Maxwell's equation, it tells you if the light is traveling in the Z axis, let's say along the Z axis, then the electric field can be anywhere on the X and Y plane. It has to be perpendicular to direction of propagation, but anywhere on the X and Y plane it can be there. But however, if you restrict the oscillation to one particular axis, let us say X axis, you will get a light polarized in the X axis. So this represents the oscillation of the electric field, and the light would be propagating either into the screen or out of the screen perpendicularly. And this is another oscillation. So now you say my mapping is, let us say this is 1 and this is 0, or vice versa, it doesn't matter, but as long as you stick to a convention. So vertical polarization represents 1 bit, horizontal polarization represents 1 bit. The whole idea is that, again, going back to our vector notations, the vertical and horizontal are orthogonal to each other. So if I take a projection of this onto this axis, it will be 0. And similarly, if I take a projection of this into this axis, it will be 0. So it has to be orthogonal to each other. I can also take another pair, a similar pair, which are mutually orthogonal, which is 45 degrees and 135 degrees. Between them, as you can see, is a 90-degree angle. So the projection of this on this, which is the dot product, will be 0. Whereas now this is the important thing. The projection of this onto this or onto this is not 0. Okay. So 45 degrees onto the vertical or 45 degrees onto the horizontal projection is not 0, or projection of 135 degrees onto either horizontal or vertical, or even vice versa, projection of horizontal or vertical onto 45 135 is non-zero. Okay, so but between this I can use as 0 and 1 or 1 and 0 as you please, and between this I can use 1 and 0 or 0 and 1 as you please. Okay, I'll tell you why this orthogonality comes into picture, because it essentially means that I cannot, when I take a measurement, I cannot mistake this polarization to be this polarization. Okay, now how do we make a measurement is this. So this is a little piece of glass. It's made of glass. Okay, and these are two, it's called a beam splitter. This particular thing is called a cube beam splitter because it looks like a cube, and here in the middle is a special coating of certain material which will ensure that this is something called a polarizing beam splitter, which Professor Jaikumar was talking about right on the first day itself. Now the polarizing beam splitter, there are two kinds. There is a ordinary beam splitter. Now what ordinary beam splitter does is, if I send light onto it, it will send 50% of that light into one direction. It will transmit 50% of light. It will reflect 50% of light. Okay, so it's just a 50-50 beam splitter. Okay, and whatever is a polarization here is equally divided into both places in an ordinary beam splitter. There is a special beam splitter called the polarizing beam splitter. What it does is, no matter what light you send, it will check what is the polarization. So if you send a completely vertically polarized light, that gets transmitted. If you send a completely horizontally polarized light, it will get reflected. It will come onto this side. And if you send a mixture of vertical and horizontal polarized light, the vertical part of it will go here, horizontal part of it will go here. So it will actually unmix both of them. Okay, this is the polarizing beam splitter. So the simple way to detect so let us say pulses are coming here. So my communication is going on. Some pulses are vertically polarized, telling that it represents bit 1. Some pulses are horizontally polarized, representing bit 0. So you put a polarizing beam splitter, you put one photodiode here, one photodiode here, and then if this photodiode gives you a click, I know that my pulse was vertically polarized. If this photodiode clicks, I know it was a horizontally polarized. So this becomes a beam split. This becomes a receiver now. The polarizing beam splitter with two diodes on either side becomes a receiver. So you can tell whether the pulse was vertically polarized or horizontally polarized. So therefore map it back to bits 0 and 1 as you and your. I'm still not talking quantum. I'm still talking classical communication. Okay, this is a free space communication. Fibers are a problematic because fibers don't maintain polarization. So fibers, they do something slightly different methodology. I'll come to that method in a minute. First, let me explain. Think of a free space communication from one building to another building. I am sitting and communicating. I'm sending pulses of light. Okay, and the polarization of the pulse are mapped to my information 0 or 1. As the stream of bits is coming in, my entire picture is divided into bits 0 and 1, converted into polarized light, and then sent across. Okay, on the other side I have this system which will detect. Okay, however, I will come back to this picture a little bit, and now this whole concept of BB84 protocol is a pretty lengthy protocol, so that's why I'm kind of in detail explaining. What we want to do is that I take the 1 amp cipher. So in the 1 amp cipher, I said the encrypted key C is equal to M plus K. M, I already have it with me, the message. and the key I'm going to generate it then and there and send it across to my counterpart on the other side. Okay, and now it has to be done in a very secure way, so that the key should not be, someone who intercepts the key should not be able to identify the key. So the key is sent in a secure way and message is still kept with me. So this is technically quantum key distribution, or QKD for short. Okay, quantum cryptography gives a little bit of a wrong impression. The whole idea is that I use quantum mechanics to distribute my key, and then I go back to my classical communication scheme, encrypt my message using this key and happily transmit it, and use the standard classical methodologies to do all your whatever you have learned in your communication, fidelity enhancement, error corrections, all of that to do. Okay. Okay, now I come to the, I still have to describe a little more about the Beamsplitter. So I said I have a pulse coming here. If that pulse is a mixture of light of vertical and horizontal, then vertical part of it gets filtered out and comes here, horizontal part gets filtered out and comes here. But there's a bit of a when I go down to single photon levels. Okay, now if I go down to single photon levels, what happens is that I cannot have a mixture. Okay, if the single photon is vertical, nothing comes here, it goes completely here in this port. If my single photon is horizontally polarized, then it will come here, nothing will come here. Okay, however, if the polarization of that is 45 degrees, again Jai Kumar was talking about it on day 1, polarization in a particular angle. Now it so happens that in a classical electromagnetic theory, I can take this, I can take a vector at 45 degrees and resolve it into a vertical and horizontal components. So 45-degree vector is equal amount of vertical component, amount of a horizontal vector. Okay, I can resolve it. Okay, so which means that if I send a light which is 45-degree polarized, a continuous light, not at the photon level, a full-fledged torchlight, or a laser beam, 45-degree polarized light, it will, this fellow will resolve it, the electric field, into two components, and it will send half the intensity into vertical direction and half the intensity into horizontal direction. Remember, this is not a mixture. This is actually a 45-degree polarized light, but a 45-degree polarized light can be thought of as a mixture, and my beam splitter will also decompose it as though it was a mixture. That is for a large amount of light, which is some 10 billion, 100 billion photons. If I make this light very, very weak, again it is something similar to what Professor Jai Kumar was talking on the beginning days. I send a single photon which is 45-degree polarized. What would happen at the beam splitter? Now again something strange happens. So quantum mechanics is a little bit non-intuitive. It's not strange in the sense, because when I write down all the mathematics I talked to you in the morning, most of the mathematics comes out very nice and it tells me exactly what happens. So this is not unexplainable. It's unexplainable from a classical point of view. The whole idea is that the photon cannot be divided into two components. I cannot split a photon. So a photon has to be integral as a photon. Then what would happen is that the beam splitter now looks at it as a 45-degree state, and the state of polarization, like what I was writing all the parameters in the morning, now state of polarization also becomes a parameter. So the state of polarization is 45-degree, and what it would do is that I think I've written it in a later stage. I've written like a 45-degree can be written as, morning I was talking about, I can write it as two different states, vertical and horizontal. So I can exactly write it as a superposition of vertical and horizontal, right? As I told you, a 45-degree vector is resolved into vertical and horizontal. In a similar fashion, a A combination of vertical and horizontal polarized light is also a 45-degree light. I'm sorry, I can't write on this one. I wish I could write on this. This is a PDF. I can't write on this. So I don't have the whiteboard kind of things. So anyway, uh, I will show the quantum mechanical notations I talked to you in the morning. I'll immediately show you in a few slides later. So the vertical and horizontal polarized light can be considered as a superposition state which leads to a 45-degree stage, and because the photon cannot be resolved, now this fellow, it becomes like a coin toss. So it either changes into a vertically polarized light and then transmits on this, or it converts it into a horizontally polarized light and reflects it. It will either come out on this face or it will come out on this face. Now, a priori, you can never tell which way it comes out. So suppose I'm sending a stream of 45-degree photons in this. All photons are polarized at 45 degrees. Some of them will come out here, some of them will come out here. And not only they come out, they don't remain a 45-degree polarized light. Whatever comes out here becomes a vertical polarized. Whatever comes here becomes a horizontally polarized light. So you call this as a collapse of the wave function. So I have written the wave function as a combination of vertical and horizontal, and it will come back to one of them. So the superposition of a combination of vertical and horizontal is no longer valid after it comes out of the polarizing beam splitter. So polarizing beam splitter, now it cannot filter, but it works as a coin toss. And this turns out to be in a statistical limit, this turns out to be exactly 50-50. So there is a company in Switzerland which has created a little box where there is a little diode laser and a fiber, and then it goes to a polarizing beam splitter, and there's that fiber and laser sends a continuous beam of single photon pulses. Okay, it's just one photon in a pulse. They have reduced it and they have checked it and cross-checked it. And here are some special detectors which can measure very low light level, a few number of photons. So every time a photon comes and hits it, it gives you a click. It gives you one TTL pulse. These are called avalanche photodiodes. It's a combination of that. So therefore you have two of them, and as the stream of single photon pulses comes, either this fellow gets a photon or this fellow gets a photon. So you get a TTL pulse here or a TTL pulse here, and then you map it to information. This is bit 1 and this is bit 0, let us say. It can be other way around also. So therefore sometimes bit 0 comes, sometimes bit 1 comes, and they have looked at the statistics of this, and they have cross-checked many statistical routines, and they have shown that this is a very good generator of a random 0 pulse 1. So they call this as a random number generator, as far as digital random number generator, not your real random number generator. And because this is a hardware fellow, this is much more reliable than any of the pseudo random code that you people have been learning about. On a computer, I can write an algorithm to generate random numbers, but most of them are pseudo random numbers because they are really not random. Whereas this fellow turns out to be very close to a real random number. There's a little bit of an offset. That's why I'm not telling that it's a perfect random number generator. Of course, nowadays you have some other things like the IBM gives you a chip where it uses the short noise limit and all those things to give you a nice random number. A hardware random number generator is always more reliable than a algorithmic random number generator. Anyway, but now the entire BB84 scheme is now based on the facts that I told you, that if I have a horizontally polarized light, it will either come here or either come here. In a similar way, I can have a vertically polarized light, but I can twist this cube to sit at 45 degrees. So it's in a twisted frame, it's as good as a 45-degree light going on to this. So I can get a, again, vertical and horizontal with respect to this, but because entire frame of reference is tilted, Now I get either a 45 degree or a 135 degree pulse. Okay, so now the protocol runs like this. So we'll call this as Alice and Bob, and there's an eavesdropper, Eve. So this has been one of the standard things used. There are some people sitting in India who want to replace everything by uh, Indian names. Call this as Aruna, call this fellow as some Babji or something, and find out a name with Eve and all that stuff. But anyway, so but most of the people, because A, B, that's basically how it started, and Alice and Bob, and just for me, an added this is a girl called Alice Liddell. This is a very old photograph taken in somewhere in 1800 by Charles Dodgson, whose pen name was Lewis Carroll, the guy who wrote Alice in Wonderland. And this Alice was actually his friend's daughter. He told her the story. So, and this is a photograph he took of that Alice. So this is, of course, a singer called Bob Marley, and this is Eva Braun, who was Hitler's mistress, just to add an additional punch to these figures. So this is how Alice is the person who generates data. She needs to transmit it to Bob, and there's an eavesdropper who is kind of eavesdropping in the middle. What Alice does is this. Alice generates a series of random numbers, okay, and she calls that as the basis states, okay, and the basis in the basis random number, let's say zeros and ones. 0 corresponds to vertical basis, and 1 corresponds to 45 degree basis. That means this is the mapping for the basis. There is one more mapping for the data itself. Okay, the data is now mixed up with the basis. So let us say this is my data. So this data is now, this is mapped to, let us say 45 degrees. So that is the 0 and the cross basis. And this is mapped to, let us say, vertical polarized light. And this is again mapped to 45 degree basis. This is mapped. So in each basis, I have 0 and 1. Vertical is 1, horizontal is 0. 45 degrees is 1, 135 degrees is 0. Okay, so I'm not only taking this is a random number sequence. This x plus is also a random number sequence. Okay, so there are two random numbers coupled into this. So we don't know a priori which basis it will go with, 0 basis. And so Alice simply transmits this. This means 45 degree polarized light. This means a vertically polarized light. This means a 135 degree polarized light. This means a 45 degree polarized light. This means a vertical polarized light. This is a horizontal polarized light. This one is a 45 degree again. This is a horizontally polarized light. This is vertically polarized light. This is 45 degree polarized light. So like that, the pulses are being sent, and the entire sequence is completely random. She transmits it to Bob. Bob doesn't know in which basis it's coming. So Bob, for every pulse, Bob guesses whether it's a vertical basis or a 45 degree basis, and then he makes a measurement. Okay, he makes a measurement and records his measurements, and he also records in which basis he has measured. Now, after the entire sequence is done, Alice, let us say, transmits about 100 bits in this fashion, and Alice will openly tell what was the basis she used, not the bits itself, but the basis. So she will simply say here cross plus cross cross plus plus cross plus plus cross. But again, it can be mapped to a set of zeros and ones, and she will simply send that digital information. Let us say 1 0 0 0 1 1 0. This is, I'm talking only the basis. So she will transmit that. Now Bob will see among his measurements where did the basis part matched with Alice's base. Bob's basis and Alice's base are same. So he picks up only those sequences, because see, look at this point. Let us say Alice has sent in a cross basis 0, so 45 degree photon. Now Bob, because he is randomly picking, he has only two choices. So he has picked up cross basis again. The moment Alice has also sent in cross basis, Bob also measures in the cross basis, this answer will be correct. It will be whatever Alice has sent in the here also, if Bob has made the cross basis, the answer will be correct. If on the other hand Alice sends in a cross basis, Bob tries to measure it in a vertical basis. So that is what I told you here. If you go back here, Alice is sending in a cross basis, so it is either 45 or 135, and I'm trying to measure it here. I don't know whether it will come here or here. Okay, now I don't know the polarization of this part. I don't know the polarization here. I only know I'm a Bob, let's say, and I only know the polarization here. So some light pulse comes and I get a detector here. I assume it to be vertically polarized because I have no idea what is the state here. I'm simply assuming that it's to be vertically polarized because assuming that Alice has also sent it in vertical polarized. So I record it as vertical. Then I check with Alice, let us say 52nd bit, I measured it in, I got an answer as vertical. And because I am measuring it in the plus minus basis, vertical basis. And I asked Alice 53rd bit, I measured in the vertical basis. She also had sent it in the vertical basis. Therefore, my answer is obviously correct because if it is a vertical photon, vertically polarized photon, there is no chance it can come here. It has to come only here. On the other hand, a 45-degree light can either come here or come here. We don't know beforehand where it comes. Okay, so I could be, when I do it in a vertical basis, I have a 50% chance that my basis is correct with Alice. If my basis is correct with Alice, my answer is also correct. Okay, if let us say she had sent a 0 bit in the cross basis, I measure in the vertical basis, and by my ill luck it went here, so I measured it as 1. Obviously that is a wrong answer. By a chance she has sent a 0 on the cross basis and I also got my photon here, and so I measure it, now I recorded it as 0. Okay, so Alice had sent a 0, although the basis is wrong, because it's a luck that it has come here, I have recorded the correct number. Okay, although the basis is wrong. Now what is the probability of that happening? It's 50% because a cross basis can 50% come here or come here. Same thing goes for 1. Alice has sent a 1, but if Alice has sent a 1 on the plus basis, it will definitely come here. There's no other way. So if my basis is correct, my answer is obviously correct. If my basis is wrong, there is a 50-50 chance that my answer is correct. So there is a 50-50 chance that my basis is correct. There is a 50-50 chance that my answer is also, basis is wrong, answer is correct. So either way, I am correct 50% of 50%. So that is about 75% of times my answer is correct. Okay, that is as far as Bob is concerned. But what will Bob and Alice do is that once the basis is matched, all the bits for which the basis has not matched, they will simply throw it away. I'll show you. I think I have a, let me see if I have that. Yeah, I have it here. Okay, so Alice has sent in this fashion. Okay, 0 plus. Bob has also measured in plus, so he will retain this fellow. Alice has sent in a cross basis 1. Bob also luckily has measured in the cross basis itself, so this 1 is correct and Bob will retain this number. Here Alice has sent in a cross basis. Bob has measured in a plus basis, so Bob's measurement sequence is wrong. So Bob does not care what is the answer, he will simply discard the entire system. Here also Alice has sent in a plus basis and Bob has measured in a cross basis, so this answer is unreliable, so Bob will simply discard it. So Bob retains only those where the bases are matching, and he has measured it as 0, so he will record it as 0. Just give me a second. भैया मैं बहुत बिजी हूँ अभी. बहुत बिजी हूँ अभी, नहीं आ सकता हूँ. ठीक है, ఇప్పుడు రాలేనండి, బిజీగా ఉన్నాను. हाँ, मेन गेट पे है, बट अभी अभी बहुत बिजी है, और 1 घंटा बिजी पे है, मैं लेक्चर दे रहा हूँ. हाँ, मैं बिजी हूँ अभी. ठीक है, आप. हाँ हाँ, कल दे दीजिए, कल दे दीजिए. थैंक यू. Okay. Okay, sorry about that interference. Okay, so now, of course, this makes one big problem. I still have not talked what happens to Eve. I'll come to what happens to Eve in a minute. Now, of course, Bob and Alice have to discard about statistically 50% of them. There's a 50% probability that this happens, 50% probability that this happens. So out of 1,000 bits, 500 randomly get discarded, randomly 500 are selected. Okay. So there is there is, of course, it's not efficient in that sense, but I'll show you in the end why this is still very nice system. Now, Eve also does not know what is being transmitted. So Eve also has no idea. So Eve also does what exactly Bob does. So Eve picks up every bit, measures it, and normally a detection of single photon is a destructive measurement, because the photodiode has to absorb the photon and give it out. So let us think of some way that what Eve does is she also randomly picks up, but she does not want her presence to be known. So she sits in the middle. That it's called man in the middle attack. Nobody knows that that person is sitting there. Okay, Bob should not know Eve's presence. So Eve will either recreate a photon which she thinks what she has measured and sends it to Bob, or let us for a moment think of some fancy measurement method scheme where Eve does a non-destructive measurement. Okay. Now here comes the whole point. Let us say for Eve measures in a wrong basis. I already told you what happens with a 45-degree photon coming into a vertical beam splitter. 45-degree photon coming into a vertical degree beam splitter will become either vertical or horizontal at the end of the day. So essentially, the polarization state has changed. This is what I think either Debjyoti or Jaikumar was mentioning, that if you measure in the same basis, you don't change the state of the polarization. So if the photon was vertical or horizontal, if it was vertical and I measure it in vertical, it remains vertical. If it was horizontal and I measure it in vertical horizontal basis, it is going to remain horizontal. But if it was 45 and I measure it in vertical basis, it either becomes vertical or horizontal like a coin toss. I don't know what it happens. Okay. Or if it is 135, same thing happens. Or if it was vertical and I've tilted this to measure at 45 degrees, same thing happens. It will either become 45 or 135, and a priori I cannot tell what happens. So I am actually, by measuring it in a wrong basis, I am changing the polarization state of the system. If I measure in the right basis, I retain the polarization state. But then I don't know which is the right basis, wrong basis. So there is a 50-50 chance. 50-50 times I have changed the polarization basis. 50-50 times I have retained the polarization basis. That is what eavesdropper has done. Okay. Eavesdropper also has recorded all the measurement that she has got. Now, Alice and Bob take a small portion of the sifted key and then they compare the values. Initially, they don't declare the values. They only declare the basis. So let us say first bit, third bit, seventh bit, 29 bit, like that. They're all matching, so they retain only that. Now, of them, a small portion, Alice says, these are the actual numbers that I transmitted. Bob will take the numbers that's transmitted. Let us say they started with about 5,000 bits. They have removed 2,500 bits, and about 100 bits, Alice will actually declare the number, and Bob will look whether he has measured exactly the same numbers. Okay, so they look now at the error rate, bit error rate, because the bits have flipped. Okay, now some bits have flipped. Okay, because it could be because of noise it could be done, or Eve has managed to change the polarization state of 50% of bits. Okay. So now what Alice and Bob will say is, let's for a moment assume that there is no signal noise, there is no channel noise. Every channel is perfect, ideal channel. So any noise that has come, noise means now a bit flip, a bit error rate. Now any bit flip has come because Eve has tried to measure it in a wrong basis. Okay. And of course, if Eve has measured in the right basis, correct basis as Alice has sent and Bob has measured, it's a lucky chance. Eve would not have changed the state of the system. But if by our luck and Eve's ill luck, if Eve has measured in a wrong basis, she has caused a bit flip. Okay. Now here is a little bit of a statistical problem. So Eve has 50% chance of guessing the basis correctly and thus measuring correctly. So about of the 2500 bits, she would have measured, she would have correctly guessed half the time. Let's take about 1000 bits. Of the 1000 bits, 500 times she would have guessed the basis correctly, because these are all statistical now. 50-50 chance. So in 500 bits, we don't know which of the bits, but 500 bits anywhere in the sequence, Eve would not have caused any bit flip. In the other 250 times, among the other 500, 250 times she would have got a wrong basis, but still her measurement would be correct. It's a fluke. Okay. It also happens with a 50-50 chance. Again, we don't know which of the bits, but 250 of the bits, there would be correct measurement. Correct measurement, not measurement, but correct mapping to the bit 0 or 1. And but about the remaining 250, that is about 25%, she would have caused a bit flip. Okay, this looks a bit funny. I mean, she has 75% of the time she has an answer. Okay, 25% of the time she has a wrong getting bit. But here is the most interesting part. Eve generates a quantum bit error rate of 0.25. And this is where everything boils. There is no way Eve can overcome this. She has to. For every 4 bits that she has measured, one of the bits, any one of the 4 bits she would have caused a bit flip. It's a statistical process. So the moment I get a single bit flip, assuming that my channel is perfect, the channel itself is fantastic, the channel would not cause any bit flip. If I get 1 bit flip, I'll immediately declare that there is an eavesdropper and she has measured 4 bits. Okay. So now I'm going to go through, Alice and Bob will sit and sift through about what is their bit error rate, not the actual bits. They are not comparing the actual bits because that becomes public. They will look at error rate, and if they look at error rate, they will know how much probability that Eve could be measuring. Okay, and these are all the same things I explained, and this is a little bit more that every I explained it. This is a whole putting in mathematics, and don't worry about all the things. That every time Eve makes a measurement, she causes a bit flip. That is the whole point in this one. Okay, and there is also something called a no cloning theorem. That means, well, it's been wrongly interpreted as you cannot make a copy of a quantum state. No, that is wrong. You can definitely make a copy of as many copies of the quantum state, but you cannot make a copy without measuring it. It's something like a pre-Xerox era. Now you can Xerox a document and claim that I have not read it. Okay, I have not read it, so I don't know the contents. I only copied it and put it up and put it there. Whereas in the pre-Xerox era, if you have to make a copy, you have to read it. You have to read it and rewrite the whole document. So therefore, you cannot say in a pre-Xerox era, you cannot make a copy without reading the document. It's the same thing here. You cannot make a copy of a quantum wave function without making a measurement. And measurement, if you are doing not in the right axis, if you are doing in a wrong axis, you are going to leave a footprint on that one. And that is why there's something called quantum non-demolition. Don't worry about that part. So so now this is what. So Eve's measurement results in a noise. So every noise that I have got, I will map it to Eve's measurement. And now I go back to my classical measurement theory and try to find out what is the mutual information. How much information actually Eve has. How much now there is, this is again because of the statistics. All the bits in which Alice and Bob are matching on their basis. Remember, only they retain that part. So this is something they don't retain. There is a very small chance that Bob's sequence of bases and Eve's sequence of bases is same. There is a finite chance that Bob is correct, Eve is wrong. Okay, and there's a finite chance that Bob is correct, Eve is wrong. Bob has measured the right number, Eve has measured the wrong number. Eve has retained it as a wrong number. Finite, 50-50 chance. Okay, and therefore, within what Bob has retained, where Bob's basis is matching with Alice's basis, and Bob has retained only that part, Bob has discarded the remaining one. Eve's basis set could be overlapping here. Eve's basis could be correct, Bob's basis could be wrong. That doesn't help Eve at all. Okay, because Bob and Alice, both of them are going to discard that bit, even if Eve has information about this. Among this, Eve has 50% information. So, and also, so the question one now computes is what is called as a mutual information between Alice and Bob. That is how much information Alice and Bob have kept non-discarded, and how much information is between Alice and Eve. It could be as well as Bob and Eve. It'll be the same thing. No, it won't be the same thing, but it's, you take only this part. Now what it says is, if mutual information of Alice and Bob is more than mutual information of Alice and Eve, this is basically the old noisy information mathematics. Okay, if information is more than the noise content, you can do a nice error correction schemes to improve it. If noise is more, all of you have done any kind of image processing will know this part. If you have done any kind of a digital protocols, even if you have learned it a little bit, you will know this. If noise content is more, there is no way I can do error correction. Okay, only if noise content is small, I can do error correction. But now what these people will turn it out as the noise content is analogous to Alice Eve information. That is, among what Alice has sent, how much Eve knows from Alice thing, and this is how much Bob knows from what Alice has sent. Okay, so if Alice and Bob have a higher information content than Alice and Eve, your classical error correction codes can improve the fidelity. And the basic idea is this: both Alice and Bob and Eve also will do the same error correction codes. Many of you have read about all your hash functions and Hamming codes and all those things, which I do. I only know the names. I don't know the whole protocols. Because of learning through this, I learned about the names of all those things. And you have some dozen error correction codes. And it so happens that Eve also can run the same error correction codes, but Eve has a more noise content in her information, so her information will not improve. Okay, I unfortunately I had one of my students had done a simulation studies of this part, and in fact we had clearly shown that Eve's information does not improve. I somehow could not get hold of that thing, and I lost it when one of my hard disks crashed. So, and this was a couple of years ago. So I wish I could show you that thing. It beautifully comes out that the improvement when we ran a Hamming code, and then the Alice and Bob the fidelity increases, the mutual information increases after running the Hamming code, whereas Eve's information remains absolutely static. It doesn't improve at all. Okay, we created some noise and we simulated this whole process. It's a beautiful result. I wish I could show it to you. Anyway, so now this is If this mutual information is almost equal, then what helps Bob will also help Eve. So Bob tries to construct his complete information using error correction codes. Eve also will try to do the same error correction code, but because Eve has the same amount of information, Eve's error correction code also will improve Eve. So therefore, what Alice and Bob will decide is that they will look at the noise level, the bitrate noise level, and tries to give an upper bound to how much information Eve may have. I'll show you some mathematics in the next slide. Okay, I myself don't completely understand it. One of my collaborators did the calculation, but I'll try to explain to it in a loose form, and some of these are in uh, um, there is enough textbooks which will exactly tell you what is all these things, the exact mathematical recipe they will tell you. So if you can put an upper bound based on the noise, how much information Eve may have. I still don't know how much information Eve actually have, but I can construct an upper bound onto it. And if that upper bound is a little more than what I can tolerate, I will completely abandon the protocol. Remember, I am only building the key. I have not sent the message yet. Okay, this implies if Eve has more information, it implies that Eve has substantial information of the key. Okay, so the key is not good to be used. It's not safe enough. So we completely abandon the key and we start afresh the whole protocol. Okay, till we are convinced that Eve's information is very insignificant. Eve may have some information, or it could as well be channel noise. And till we are convinced that Eve's information is not dangerous enough, we don't use this key. Okay, of course, this can cause you a denial of service. Eve can go on interrupting as much and create a denial of service. We can't help that one, but it doesn't help Eve either. Okay, someone who wants to really learn secret, it will not help if you already know that someone has learned your secret. Okay, you can as well abandon the whole thing. Only if you go ahead with your protocol not knowing that somebody else already has your credit card number, then the other person can crack in and use all the stuff. Okay, so abandon is not going to help either Alice, Bob, or Eve. So once we know that Eve's information is less, we can do classical error corrections and improve the key. And once I establish a key, I can encrypt my message and send it across on public channel. And the whole idea now you have seen is I have made sure of one thing. First is that I'm going to use the key only once. Okay, the next message I have to send you, I'm going to generate a fresh key, share the key with you, cross test the key many times to sure nobody has intercepted it, and then I encrypt the message and send it to you across. I can afford to lose as many keys as possible. The disadvantage of the system is that if I have to create a 128-bit key, I have to start at least with a 2000 or 10,000 bits because I'm going to discard many of the bits across. And there is also a possibility of a denial of service attack by Eve, and well, that creates even more headache. And of course, the entire protocol may take about half an hour or an hour to finally get a good, nice, sifted, filtered key. And but if the message is worth going all this trouble, you better do it. Okay, and this is definitely safe, proven safe than RSA key. RSA key is easy to use, but at some point of time it can be vulnerable. This thing is definitely not vulnerable. There is no vulnerability in this, but of course it takes time to make the more thing. So therefore, in cases where really security is extremely important, it may not, you may lose about 20,000 rupees that's in the bank. The best is to withdraw most of the money and keep it with you, so that even if you lose only a small amount of money, but sometimes it can be dangerous. It can be a safety issue. It can be safety of the nation. It can be, or even millions of dollars. So if it's worth it, go through the quantum cryptography. Okay. This mathematics, it's also a little bit difficult for me. As I told you, one of my collaborators many years ago taught me this and I've forgotten parts of it. But this, as you can clearly see, it depends on the Shannon entropy. And one can go through this. There are some references which you can look at it. It will give you the whole way of calculating. I think there is a paper by Shore and Preskill which explains this whole thing. So from the Shannon entropy, I can essentially calculate Shannon entropy. I already told you in the morning. That will tell me how much of information content can be put in. Although Shannon entropy is always thought or expressed or described as an entropy, that is how much of uncertainty I have in the information. It can be kind of twisted and say how much of information I can pack in, let's say, an 8-bit word or a 16-bit word or a 128-bit word, how much of information I can pack. Okay, and from there I can essentially compute the mutual information. And Eve does not measure all the qubits, because if she measures all the qubits, she will betray her presence. So therefore she will measure as little as possible. And if she measures all the qubits, then your mutual information for Eve is 0.25. So therefore this h of d is actually a noise case, but now we'll use noise as information content of Eve, and you will end up getting about 0.19 bits per qubit. Okay, and from there we calculate a deterministic information, and which means how much information Eve can actually have. So if it is 0.5, that means both Alice and Eve has exactly same amount of information, the protocol gets abandoned. Okay, so abandon will not help Eve. So she measures just short of this, and then this is what two people called Shore and Preskill came about, and they have explained in detail in their paper, and they came up to about 17% noise per qubit. Essentially means that Eve has a lot of information, considerable amount of information. So I don't even want to know what Eve is doing. I only look at my noise rate. I look at my noise rate and say if it is more than 17%, whether Eve is there or Eve is not there, I assume that there was an Eve and she has enough information, so I abandon the complete protocol if errors are more than 17%. So that looks like a very nice number. So if I take the entire sequence and I take a part of it and do a comparison between Alice and Bob's data, and you see how many bit flip errors have happened. If that is less than 17%, protocol is reasonably safe. You do a normal error correction and you use the key. If the error rate is more than 17%, you assume that the Eve has a lot of information, so you simply abandon the whole protocol and you happily not happily, rather unhappily, you discard the protocol, you start the whole process afresh. You try to generate a new key now. The biggest advantage of this is that the key is generated then and there. It's not like Alice and Bob have shared a key, kept it in the safe, somebody has seen the key and then already made a copy of the key without Bob knowing it. There's no such danger at all. The key, and somebody can hack your computer and take off the key where you have stored it. Your key ring, all the key ring, that is something called, it's always prone to hackable, it's vulnerable. So now what you have done is your encryption key is being generated a few seconds before your protocol has started. In fact, a few milliseconds before the protocol has started. So you definitely know, and the key is obviously a sequence of random sequence of zeros and ones. You definitely know that the key is reasonably safe. Nobody has hacked it. And Eve has intercepted, but Eve hasn't got enough information, so it is safe enough. So now you can use the key. So this is the whole idea of a quantum key distribution. And of course, the quantum part is very, very small in this. The quantum part only comes in the fact that because I'm doing a single photon level measurements, any measurement done by Eve, any intercept by Eve leaves a footprint. I cannot prevent Eve from intercepting, but if Eve has intercepted, I can know that Eve has intercepted. And not only I can know Eve has intercepted, but using this classical information theorem, I can actually compute how much information that Eve may have at maximum. I can have an upper bound on the amount of Eve's information. Is that dangerous or not dangerous? Based on that, I take a call whether I have to abandon this protocol or not. So that is the best part of this, the quantum key distribution scheme. At the end, I'm convinced that Eve has no significant information to cause harm. Okay. So, sorry, was there a question?
కంప్లీట్ గా కాలేజ్ సార్ అమ్మాయికి సేఫ్ అండ్ సెక్యూర్ గా ఉంటుంది కదా, సో అందుకోసం అనేసి కాల్ చేశాను. సో అమ్మాయికి హాస్టల్ ఇక్కడే ఉంటుంది సార్, మీరు బయట
Sorry, getting some other information on your mic. Okay. So again,
participants, please mute your mic.
నేను కూడా సిఎస్సి ఫ్యాకల్టీనే. అమ్మాయి సిఎస్సి కదండి సార్?
hello. Okay. Anyway.
Sorry for the disturbance, sir.
Yeah, it's okay, no problem. These things can happen. Okay. And I'm not going to go detail into Shannon entropy and von Neumann entropy. I introduced to you, and I'm only trying to tell you that this, the so-called hollow bound, which essentially the information Eve can extract, is limited by the hollow bound. So the whole significance of why I introduced the entropy calculations in the morning, so that will now give me the accessible information. So this becomes very important in a quantum key distribution calculation, because you are forced to calculate either Shannon entropy or a von Neumann entropy, and then find out how much Eve has information. Okay, I'm not going to go into details of this. There is a little bit of a issue in between the theory and the actual experiment. So people have done experiments. This was proposed as a theoretical framework in 1984, and later on in the 90s, end of 1990s and in the beginning of 2000, many people tried the actual protocols. In fact, today there are commercial schemes which have been doing it. There is a small issue in the commercial scheme. The commercial scheme, what they do is they use a diode laser, and then they put a lot of filters to cut down the intensity of the diode laser and claim that I have a single photon source. This is something I cannot explain in the purview of today's talk. This is something which goes into a deeper mathematical this thing, that the diode, any laser, any theoretical laser, the nature of the light coming from a laser is slightly different from a nature of light coming from, say, a torchlight. So I can create pulses, and I can ask a question like, how many photons am I getting per second from a laser? In a normal, even a normal pointer laser that most of you have used or aware of, you have about 10 billion photons per second, and then you can cut down by putting filters. You can reduce the number of photons that is coming out to close to single photon level. But the problem is that typically I will not always have single photon. Sometimes I'll have 2 photons, sometimes I have no photon, sometimes I have 1 photon. So it's kind of equal. So it does not really become a proper single photon source. That beam splitter, whatever theory I have told you, is meant for 1 photon only. What happens when 1 single photon comes near a beam splitter, and because the 1 photon cannot become into half a photon this side, half a photon this side, it has to go as a single photon. So it either has to come on this side or it has to go on that side. Okay, so that is why all the things become. And so don't worry about the next 2 lines, and these are just for something that I had written long back for people who have been involved in the mathematics of the quantum the laser source and all stuff. So makes it vulnerable. But for engineers, this is the bigger problem. For engineers, the bigger problem is that my fibers, optical fibers, are not uh, polarizing, maintaining. I am not going to explain to this, but a slight rework is done in terms of pulse time propagation. So it is not involved in polarization maintaining, but in terms of uh, bit in a double split path, whether the two pulses come, I send two pulses with a fixed time width. Do they come a little before? Do they come a little after? Because I randomly send it either in a path 1 or path 2. If it goes in path 1, the two pulses come closer. If it goes in path 2, the two pulses go a little far away. And then by measuring those kind of things, I can overcome the polarization problem. But the entire mathematics gets more or less mapped easily onto that. Okay, but the bigger problem that happens is that when I'm in the communication band, the C band or something, which is 1300 1.3 micron or 1.5 micron, which is where all the fiber optic communication happens, my single photon detectors, the low photon detectors, are very inefficient. They are made of gallium arsenide and germanium and stuff like that. So the efficiencies are 15% and 20%. That means if I send 100 photon onto the detector, these are avalanche photo detectors, and my detectors will typically measure 20, so I lose about 80 of them. So if I have to build a key of 100 bit, if I have to forget building a key of 100 bit, if I have to measure 100 bits, I at least have to send 2000 bits and then 1000 bits, and then it will only measure 100 bits of this. This is a slightly older information. Now the technology has improved a little bit, but not too much. My photo detectors, avalanche photo detectors, still have not crossed 40% detection efficiency. So when I'm sitting in a fiber doing a quantum key distribution, this becomes a big problem. It puts a lot of things on my efficiency. So which means that I have to send, although I can always discard photons which I have not measured, but I have to send more photons to even make a 128-bit encryption key. Okay. There is a way of workaround. You mix 1550 with a strong 980 nanometer to get a 570 photons at the detector. The silicon photodiodes at the visual things are slightly better off, but still it has its own issues. Nothing is perfect. There is no free lunch anywhere. I always have some problem, and I'll have to overcome this, which of course engineers who have worked in communications already know that your system is never perfect. You always do a multiple no again you do, normally you send same information multiple times so that you overcome any channel losses, but now you are a problem. You cannot do that because Eve could measure some photons in one run, and you could measure some other photons in one run and build up the whole information. So you cannot simply send multiple bits, what do you call the copy bits, and then say I've overcome noise. That doesn't happen in a quantum key distribution. It works in a regular communication. Okay, so you have all this problem. And some people also tried looking at where I cannot have a fiber. So let us say I want to do between I want to do between a military tank and a headquarters. Okay, and I want to send some data, or all your laser guided missiles. Missile is going. I cannot attach a fiber to that, or I can communicate ground to satellite or something. So this has to be free space, and in free space what you're seeing the graph is a transmission. This is a calculation from NASA. This is a theoretical calculation, wavelength versus transmission. So you can see transmission drops huge. This is a decibel scale. Transmission drops huge in certain wavelengths, whereas in certain wavelengths the transmission is almost completely 1%, 100% transmission. So there is a transmission from 780 nanometers close to about from 713 nanometers to 800 nanometers, a little below 800 nanometers. There is another window between 850 nanometers to, this is micron, so 850 nanometers to 900 micron. And this calculation is not shown here. Actually, something very nice is that at 1.5 micron, 1500 nanometers, there is a reasonably good window. So I can as well use the same 1500 nanometer. But even here, 780 nanometers is fantastic because all the diode lasers that go into your CD drives are in this region. 850 nanometers are also fairly available. They are all cheap diode lasers and low power, and you can happily use it. And then you get a variety there called VCSEL, VEXEL, vertical cavity surface emitting lasers, which actually can be modulated at gigahertz. You can pulse them at gigahertz, so you can send gigabits a second, and you can do quantum communication with that in a free space. The big problem comes at the detector side. I'm getting few photons. How do you measure those kind of things? So people have tried something. I initially, some point of time, I also attempted it in my lab, but then well, the PhD student had a fixed time he had to finish, so we did something. He did something in free space communication. After that, I kind of abandoned the system, but maybe sometime later I'll pick it up back again and build a quantum key distribution system. But the problem is that it has to be a multiple things. We need to have a set of communication engineers, cryptography experts. So one fellow sitting doesn't work. So there have to be multiple experts have to join together, and such systems can be built. And of course, as of now, Indian government, ISRO, DRDO are all looking out for such commercial systems, even modules of the commercial systems. But then people have been busy for quite some time, as early as 1900. There's a group from a group in Geneva University started a startup company long back, before startups became very kind of thing of the day, and it's called ID Quantique. They're still running. It's a very big company. They're selling a lot of instruments. This is something which kind of shut down. It was there for some time. It's a Boston University, Harvard University. They tried to make a huge this thing. They had some success, but they never commercially exploited it, or if they have done, I don't know. There was another company called Clavis based in New York. This information is also old. There is a company in Bangalore. It's called QNU Labs, QUNU. That is a spin-off from a professor in IIT Madras. His name is Anil Prabhakar. It's a spin-off from him, and they have just started about last year or a year before that. They released their first product, and I don't know completely as to if how is their product. Is it selling? Have people been testing it? Basically, they all claim to be something like a plug and play. That is, you just plug it into your normal communication network, and it will give you an overlay of a key generation, a key distribution using quantum key distribution. As a physicist, I know some shortcomings of that thing. They are not telling us. I have talked to people sitting in QNU. Since they are a commercial company, they are not divulging a lot of secrets, even to me. I mean, I personally know Professor Anil Prabhakar, but he doesn't. Some things are kept hidden, so I keep my fingers crossed as to how much they are coming close to the theoretical good encrypted or fidelity thing. But nevertheless, it's still a good attempt, and somebody has to develop protocols to check how much of eavesdropping can we actually do, and then how safe it is. The safety issues of the encryption still needs to be tested. So there are commercial attempts, and this is one of the big commercial things of the quantum mechanics that way. And of course, there are books and papers you can read, and there are better, even more papers. I'm only quoting you up to 2002 papers. There are lots of papers. So I know I took it a little short thing, but so please, I thank you for listening to me, and then questions, comments, doubts are welcome. Thank you very much.
Participants, please unmute your mic, and if you do have any doubts, you can take it. Participants, am I audible? So it seems
everybody is very clear.
yes, sir, yes, sir.
Hello, sir. Sir?
Yeah, tell me.
Please,
No,
tell something about quantum key distribution in some a little bit statistical. Actually, yeah, you said that there is a lot of statistics, etc., etc. Something,
Yeah.
if you light on this, then it will be helpful.
Okay, thanks. Maybe that'll take a little longer, so I kind of and also I am a bit fuzzy on that part. So both of this I kind of skipped on that, except for showing you the statistics comes in calculating from the noise from the Shannon entropy. How do you calculate what is the information that Eve may have? The basis of that is this: for every a single bit flip that I measure, okay, the error rate, a single bit flip that I measure, I am going to claim that maybe Eve has measured 4 bits, okay, and that has caused a single bit flip, 1 bit flip for me. So from telling that Eve, the 3 of the bits Eve has a complete information, okay, and so I try to do an upper bound on how much information that Eve has. And if that is more than 17%, I claim that it's going to be dangerous. Rather than me claiming it's dangerous, Shore and Preskill have shown that anything more than 17% is dangerous because Eve has too much of information. Okay, and if I do a classical error correction code on my side, Eve also will do a classical error correction code, the same error correction code on her side, and improve her information also. But if Eve has lesser information, even if she does a classical error correction code, it's not going to help her. That is the whole idea there. Okay. That I'll try to find out. Yeah.
So I am Dr. Mukul from Bardhaman College of Engineering.
Right. Okay.
So it's not my doubt, but I'll just share my experience of the talk.
Sure.
So personally speaking, I was a layman for quantum mechanics and all.
Okay.
But my experience of today's first session and second session is you have kept it to the simplest level, and because of which I could gain some understanding. I don't expect I'll be understanding everything, but it was a fair enough understanding of the topic, and it was a really nice experience. Thank you for that.
Thank you. Thanks a lot. Thanks a lot. It's good if I've done that little bit, it helps me because a lot of misunderstandings happen, and now I'm sure in the next couple of days, whoever gives the talk, now you'll be able to easily make out most of it.
Yes, definitely. Other participants, any doubts?
Hello, sir. No, it's not a doubt, sir. Today's this talk is very informative for me.
Thank you.
And insight into cryptography is also very good, sir. Thank you, sir.
Yeah, it's very welcome because now it's time that computer scientists get into this. I mean, physicists, computer scientists, electronic engineers form a team to really achieve the cryptography systems. It's doable, but we'll have to do it. It takes a lot of effort to get it running.
Thank you, sir.
Plug and play. It takes a lot of effort to get it running.
Sir, I think there are no more doubts. So
Okay.
I would request one of our senior faculty members, Dr. Deepak,
Sure.
for proposing vote of thanks. Deepak sir, please.
Yeah, Mukul sir, am I audible?
Yes, sir.
Yes, yes. So, honorable speaker of the event, Dr. Ashok Udayagiri sir, respected principal, Dr. JVR Ravindra sir, head of the department, Dr. PS Rao sir, faculty members of the department, participants, ladies and gentlemen. It's an honor for me to propose a vote of thanks at this great event. I'm Professor K. Deepak from Mechanical Engineering Department, Vardhaman College of Engineering.
Right.
On behalf of the organizing committee, I would like to thank our eminent speaker of the today's program, both the sessions, morning and evening. Once again, Dr. Ashok Udayagiri sir from School of Physics, Central University, Hyderabad. And really, it's a great experience with sir about this quantum computing. And sir has made it very interesting. And even as Mukul sir told, it's very interesting for even a person who is attending for the first time. So we are thankful to Dr. Ashok Udayagiri sir, not only for spending his valuable time in sparing with us, but also for enlightening us with his inspirational talk on this subject. So thank you very much, sir.
Thank you.
I would like to thank all the department faculty members who are with us and supporting us from the background and making this event a successful one. And I also thank all the participants who are patiently listening and being with us. Thanks a lot for all the participants. So once again, I would like to thank all the people who are here with us. Thank you one and all. So once again, we will meet again tomorrow morning at 10:30. Thank you.
Yeah, from my side also thanks, and also thanks for having me here, and thanks to your technical team. You have made the whole thing very perfect. You've taken a lot of effort. Good. Thanks you. Thanks a lot.
Thank you, Professor. Thank you very much.
Thank you. Right. Logging out now. Thank you.